Thanks, everybody, for coming to the talk. I know I stand between you and lunch, so I'll make it interesting. My name is Sundar. I'm with Micron. My co-authors, Suresh, Sujit, and myself, we work on storage. So today we're going to talk about storage, specifically SSDs. Maybe about a year and a half ago, we asked a question. A lot of us, here wonder. So the question was, what is the role of storage, and more particularly flash, within AI, right? So we all wondered this, and the first order answer always comes out to be, hey, with AI, there is going to be a lot of data. This data has to go somewhere, and therefore, storage will grow. As I recall, Suresh pointed out in his talk, the story around memory is fairly clear. You have GPUs have HBM, and we are trying to fit as much memory as possible into these HBMs. So the question is more specific to storage, and we went forward, trying to look for some answers. And one of the answers that you heard yesterday from Micron, again from Katya, Sujit, and Suresh, they talked about how with the increasing data set and even the increasing model size, we were able to use storage to offload that and save in cost, and in certain cases, the batch sizes. So that is one use case that we have talked about. Now, over the last 3 days, and specifically yesterday and today, there has been a lot of talk on data ingestion, which we also believe is very key problem statement. So this is kind of the other phase that we are going to talk about, right? Now, that brings to the topic of, so the question of what is the role of flash or SSD in AI is now, for this particular session, we are going to talk about a specific use case, which is role of flash in data ingestion within the AI pipeline. Now, the lead-in talks have set a very good base for this talk. So there are a couple of things I had to kind of shift based on the talks that have come before. So I've kind of adjusted a little bit. I want to kind of give a highlight of what we are going to talk about today in this particular talk, which I've clarified as it's got to do with data ingestion. We are going to take a specific example, which is deep learning recommendation model. So not LLMs, but deep learning recommendation models. The other thing that we are going to talk about, we are not talking about inference here. We are going to be talking about training, okay? The last thing you will see as well is you will see data based on benchmark runs, and we will kind of share some of the findings that we have from that. So that's kind of the structure of my talk. To be more specific, I'll start with the key takeaways. The way I've structured it is, I will try to give the key takeaways, and I will try to substantiate each element of this as we walk through the presentation. The first question we are going to ask is data storage and ingest, key part of the AI pipeline. Again, we'll go through an example, and I'm going to lean heavily on Meta's work in this area. About 4 or 5 years, Usenik's presentation has set up this space really well. So I'm going to kind of walk through the case and point they make, and that would set up and answer some of the questions we are trying to answer here. Now, how flash storage plays a key role in solving storage capacity versus I/O bandwidth scaling challenge. Again, we'll go into that a little bit further. Those two items are going to, as I said, lean on Meta's work quite a bit. The third item or the fourth item would be results from storage trace analysis. So this is where we take a deep learning recommendation model benchmark, we do some pre-processing, and we do the training, and we present some results. And of course, the last one is a call to action where we want to get the industry's help, hyperscalers, everybody who works on this, to enhance existing MLPerf DLRM benchmark. Because I will highlight the characteristics that the data centers bring to this, and what are some of the characteristics that are actually captured in the benchmark, and they don't match up 100%. So there are some things that are wanting, that need to be filled, and those gaps are some things that I'll highlight. Okay, so starting with key takeaways. Again, before I go forward, I will walk through some familiar sites from previous presentation, so just bear with me. I'll try to highlight things that that I think will add value to whatever you've heard before. Data storage and ingestion is a critical part of the AI pipeline. I'll walk through some arguments, and I'll walk through some use cases which will establish this. The specific example we talk about is deep learning recommendation model. So you will hear me call it DLRM quite a bit. So that is the recommendation model systems. Training presents key challenge to storage capacity and I/O scaling. We saw that in the initial slide, and how flash storage is key to tackling this problem. And then, of course, MLPerf training DLRM benchmark will capture the training portion and the pre-processing portion of the model. And as a call to action, as I previously laid out, there are gaps that would be nice to actually fill in. Right? Okay, so we've seen this, and I'm very happy that a lot of talks have focused on data ingest, because it truly is actually a big problem, and I hope I can convince you of that as well. So this is a very simple pipeline. The pipeline is going to get a little bit more complicated. So the AI models and accelerators are often the focus of training pipeline. I think the previous speaker this morning said it. This is perfectly true. We talk about, how do we store this? Can I fit it in HBMs? Can I offload it to DRAM? Quantization effects. Can I bring it down? All those are talked about quite heavily. But when you want to turn this into some sort of a revenue, you have to go into a production side model, and that's where kind of it gets difficult. I'm going to use this term DSI throughout the presentation. This is a term I picked up from the paper itself, but it's explanatory, and I thought it's very good to use. So the data storage and ingest portion of the pipeline is equally critical. Why? I mean, why do we think that? Again, to repeat some of what we have said before, I think the Microsoft talk had brought this out. Yes, data is growing, but more interestingly, what's happening, we'll see in the next slide as well, is all of what we thought we're going to write it once and read many times now has become read many, 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 many times, right? So that is the biggest thing. Yes, data is growing, but the number of times we go access and pick up this data is grown exponentially because of AI. Okay, that's kind of one of the key things, and that's why DSI portion of the pipeline is important. The other thing that everybody knows about is you really want to keep the beast fed, correct? The GPU needs to be fed. Don't starve it. You're going to be losing money. There's a ticker running, and you want to feed it. So I think one of the morning talks essentially talked about how optimization criteria changes, and that's really that one. DSI is designed to feed the accelerators without stall, and in this talk we'll focus on storage and the ingest portion. And again, we're going to be specific to DLRM training pipeline, not LLMs, and only training. Okay. So I know a lot of us are familiar with recommendation models. We get hit with them on Netflix, Amazon, Facebook, wherever you go. They're trying to get us to do something, right? Buy something, watch something, right? So this, the recommendation models, I call it our backbone for a lot of these companies. This is what actually brings in the revenue. This is feeding research. This is feeding a whole bunch of activity that they can do because of that, correct? So this is a huge thing. And I don't know if I can walk down, but I want to point to the plot on the very right. That's taken out of a paper. there's some very interesting details, but what I wanted to point out are kind of the 4 layers there. If you see, there is a bit of sparse features and dense features, and the sparse features will look up an embedding table. So just like LLMs, you have embedding tables here. Then you have the neural network layer, which everybody is familiar with, and there is something called interaction. So how are all these features going to interact with one another to make a decision, for instance, hey, will this user click on this advert? That's an example. I'm sure there are hundreds and thousands of examples, use cases for it. But so at the end of the day, you want to predict, one of the examples is you want to predict whether the user is going to interact with any content you put there, and then based on what comes out of these recommendation models will show up in front of you, correct? So that's the key thing. Now, yes, we have heard about LLMs and how these models are very big, very large, but let's kind of take a look at how this DLRM stands up. So one of the things that perhaps I want to highlight, and I'm not sure if it came up in the previous presentations, we always think of training as, hey, we are done once and we are done. Like we dust it off, we keep it in the shelf, anybody wants it, just pick it up. That's not how it's described. DLRM models are trained every day, and that's also true that DLRM models are fine-tuned, but I'm also talking about training, correct? The DLRM models are not one single model like the foundational model, ChatGPT 3 or 4 or Llama 3.1. It's not like that. There are probably 20, 30, I don't know. There's, multitude of models as well, okay? And you can see why this is, right? Every time user interacts, you're adding data, and you want to use that in an appropriate way. Therefore, you have to fine-tune and even make your model better. So the key thing I wanted to, kind of get across in this slide is multiple DLRM models are maintained and new models are continuously trained and developed. And I talked about the model parameters. There are 2 components, the MLP and the embedding tables. And if you look at their paper, one of the paper count that they have about 12 trillion parameters in their model. That is trillion, just like our 1 billion model or half a trillion model that Llama released recently, correct? So it's a trillion model. The size of the embedding table is ridiculous. It's about 96 terabyte, and this is 5 years old. So I'm sure it's grown by another order, right? So it is 96 terabyte, but when it is compressed, it is 24 terabytes. So one of the problems they deal with, Meta deals with is, where do I put it? Like, what portion of it do I put it in HBM? What portion of it I put in memory? That's not what I'm going to talk about, but now the more important thing I want to also talk about is these models are trained on petabytes of data. I think Pratik mentioned it in his talk quite a bit. So petabytes of data. So in a couple of examples, they give like 25, 30, 40 petabytes is what they said, again, 5-year-old material. So you can imagine how this thing would have scaled since. So scalable DSI. DSI is the data storage ingest, is critical in transporting these petabytes of data to the accelerator. So I hope with that slide, I hope I've given a motivation to say, hey, DLRMs are important, very important, and that this problem statement relating to DLRM is something that we need to look at, correct, as storage flash people. Okay, so as I said, now I'm going to build on that AI pipeline or the simple skeleton I had. And there are 2 things I want to highlight here. The first thing is the first line, that is DLRM pipeline is a feedback system. And I think, again, I've seen others say the same thing too. What I wanted to say is, the key thing I wanted to say there is, whatever you're observing from the user now is being fed to train or fine-tune, rather, your inference model that you have currently. So that's continuously going on. But the more important thing is, you're going to record user interaction. So if you see the second blue, I'm not sure if, okay, cool. So if you see that, you're going to record user interactions. That's going to feed the fine-tuning, but it's also going to go into some storage somewhere, correct? So it's going to be stored, and we'll see where it goes. And then, of course, generate offline data set, meaning some cleaning and stuff like that. And then it goes and stays in disaggregated storage. Now, as the volume of data grows, something cannot be held just in one data center. Sometimes you have to go off data centers, and they talk about those scale of problems that as well. And then this petabytes of data is gotten over a fabric, they're pre-processed, and then trained on GPUs, and there was a lot of talk about periodic checkpointing as well, right? And that's a very critical problem. Now, the line that I've drawn as select models are promoted, what I'm trying to say is a lot of models get trained. Every engineer gets to train it, and then they combine those ideas, and if it stacks up to whatever metric they want, then it gets promoted, right? So there is a huge cycle that runs continuously, not once. That's kind of the thing. The other important thing that I want to distinguish based on what I know is DLRM training is a single epoch process. It is not multi-epoch. You almost never read all the data because you have tons and tons of them. So you go through them once, so the 25 petabyte is never recycled in that training job, okay? So single epoch, and that poses a huge problem, okay? Because if you are interested in tiering, if it is multi-epoch, you can do something about it. Single epoch, you have to do something, slightly different, Petabytes of data is read out, I think. Okay, the last point I wanted to make here is about how the problem statement is structured, correct? And now, in production scale, one of the ways to look at, or at least I would say Meta looks at it and frames the problem would be in terms of power, right? I have 100 tokens of power. I have to give 20 for storage, 20 for pre-processing, and 60 for GPUs. But their metric would be, or optimization criteria would be, hey, can I transfer 90 of them and keep only 10 for the rest? Why? Because those GPUs are staying there. They need to be fed. If you cannot stay within the power envelope, the number of GPUs that you can work at the same time is going to drop, and that's not good for their business, correct? Any data center business, that's not good. So the key thing, the reason I'm talking about this is that total power budget involves power of storage, power for pre-processing, I should say power for storage, power for pre-processing, and power for trainers, correct? Trainers meaning the GPU. This whole thing has to make sense and add value to their business, okay? So that's the, okay. The other thing which I did not mention previously in greater detail is essentially that they talk about how user interactions are logged and stored in a particular database. So there are like two-stage process that really happens. Everything that comes are logged in, and then a little bit of cleaning happens, and they use RocksDB and databases, and then they pre-process it and store it in another place. So we'll get into that data. Finally, when they store it, they use like the distributed file system. So they store it in distributed objects, which is compressed format, stored in distributed storage rigs, and often it's exabyte scale of storage. That's where they're drawing all this from. Storage and IO bandwidth needs, okay, here is the challenge, and we'll get to that in the next slide, really. The challenge now is we saw the data is increasing, right? But what else is happening is the number of people kind of trying to read that data is also increasing. Not number of people, but let's say number of jobs that are trying to use this data has also increased, right? So that leads us to this chart. And again, I've given the credit to Meta's paper. Please refer to that. Wonderful read all through. And I think this graph on the on my right, but really the left, actually showed up in another presentation, Pratik's presentation as well. But going to the first chart, that is the chart to your left, the data storage size has grown 2x in 2 years, right? So you have to provision in the data center, increasing capacity and keep up with that cadence of growth. The other thing is I/O bandwidth, and as you can see, the I/O bandwidth actually has increased 4x in 2 years. Again, why? Because this data is being read much, much more often to train multitude of models, specific even to DLRM, right? So a scalable architecture should meet storage and I/O demand. So they talk about this kind of, what should I do? At the lower layer, which we'll see in the next one, they have HDDs. Their question is, should I keep adding HDDs alone? And do I need another layer in order to feed this AI pipeline? Questions of that sort. That's the idea that what I mean by this storage and I/O demand conundrum. All right. One of the things that leads them to this is, of course, the scaling paradigm, scaling in data and I/O bandwidth paradigm. But the other thing is when they looked at their DSI, which is their data ingest pipeline, they found that about more than 50%. So the blue and the light blue and the solid blue, which comprises of storage and preprocessing, takes up more than 50% of the tokens, really. So they were like, okay, this is not something that I can, I can handle. And we'll talk about how their pipeline is actually set up. But greater than 40% is spent on storage plus preprocessing, which effectively to them means, less power for trainers. So Meta solves I/O scaling problem with SSD caching layer over Tectonic. So Tectonic is their HD, it's actually a file system, but usually, underneath is HDDs. They added this SSD caching layer specifically for AI training, specifically for DLRM training. So that kind of encapsulates the size of the problem. That's kind of what I'm thinking about. And that scaling or the caching layer is called Shift. Data in Shift is not durable. Shift leverages everything that Meta has already built or was building, like it uses CacheLib and it uses Tectonic file system. It's kind of integrated into it in a unique way. I'm not a kind of a file system strong software stack guy, but it's a lot of great information in that paper that I would highly recommend. And they say that Tectonic-Shift saves about 29% of power relative to using HDDs alone. I tried to get something much more descriptive. I couldn't kind of filter the data out in a way that I wanted, but the paper has a lot more detail. Okay, so having said all this kind of, hey, there's a problem with I/O bandwidth, there's a problem with capacity scaling, a lot of people are reaching for that data. So how did they actually do this, right? Like, what does this flow actually look like? So the first bit here, so I don't know if I'm okay to walk. So I want to kind of focus on, I've given 1, 2, 3, 4, but let me walk here. So this is the bit that kind of flows back. So this is the logging device. This is from their paper. So the logging device picks up everything that the user is interacting with, and it's kind of getting written into some sort of a data warehouse table partition. So two things happen. This log device is used for fine tuning, and this is also then comes into this data warehousing, and subsequently they are striped in columnar format, and they're put in the Tectonic file system over which there exists the Shift SSD caching layer, right? So this is the key thing. Now, here is where the trade-off was to be. They can, by adding drives, HDD drives, they are able to get capacity growth. But in order to get the I/O bandwidth, they have to add 2x more, 3x more. There is a number there. I'm just giving some numbers here. But so the caching, instead of moving all the way to SSDs, so this hybrid approach is what works for them. And there are metrics why it works for them. So this is where actually the training data sits. All the training data sits here in the Tectonic. And by the way, Microsoft speakers from last evening had something very similar. They said it sits in the object store. It sits in these blobs. Exactly the same thing. Nothing too different. And then, of course, the second, okay, so I think I compressed. Okay, the data here is compressed and stored in chunk stored. A lot of times it's in like a Parquet-like format. And the caching, how they do the caching, we talked about this where, it's a single epoch training. Therefore, the caching itself has to be very clever that it goes across training jobs and sees what data are commonly used, and they find out that there is a lot of data that's being commonly used, and that's how they are able to cache. Not on a single job level, but across job levels. That's the key there. So this tackles the scaling challenge that we talked about. Again, the key thing is they added this SSD caching, maybe 2023, 2022. That's the time frame they call that they went into production. The third bit is the pre-processing stage, and there is a huge description of how they organize it, and there is some neat analysis on this. But really, you take these splits, that is small chunks of batch data, you go through these DPP workers, extract, transform, serve, and goes to the training cluster, okay? And there is scalability here in that the nodes can be increased or decreased based on how much bandwidth is required from the GPU, and they have kind of a calculation of how much bandwidth needs to be. Now, one of the things I want to say is they still rely on HDDs, but for a lot of AI training, they are trying to get the data out of this SSD caching. So, sorry, go ahead. Yep. It is data dependent. So if you're taking a file and a column, certain features are used by most jobs more often, and certain periods of days or things are more used and filtered than anything else. So that's how they think about it.
So it's something that depends on what data is coming in.
It's based on the fact that a lot of them are DLRM training data. They all use similar set of data, but they could be using different features. They actually collect, according to the paper, they actually collect like 10x more than they use. So there's a lot of filtering that is happening as it comes from storage all the way to there. And they have, the paper also talks about how the filtering works, meaning that you could filter at storage, you can filter at DPP, and they talk about what are the trade-offs. But the key message is a lot of the training now goes through this caching layer, and that's the key storage, right? Ingest problem, you needed SSD, and the SSD exists, and I think I heard something very, very similar from Microsoft as well. The final one is the goal of the pipeline is to really keep the training cluster fed without stalls. I mean, that's as simple as that, their metric. Of course, within the power limit. Okay, so just to summarize, the reason I'm calling this out is we're going to compare against the benchmark, and we are going to do a bit of compare and contrast here. So Meta's DLRM pipeline, data stored in columnar format in a distributed file system. Significant portion of the DLRM data is read out of SSD caching. I wish I had a better number than saying significant portion. I kind of tried to look through it. I couldn't get it, but it has made a significant impact that it's gone into production, so I made it significant portion, right? So it's a little bit of an asterisk, or you can underline it for later. The inline pre-processing of data includes, okay, this is something I didn't mention in the previous, I should. There is a lot of decompression happening. There is a lot of decryption happening. There's a lot of transformation happening. And the transformation depends on whether you are dense feature, whether you're embedded vector. There's a lot of stuff happening in the DPP itself, right? So I think Pritesh, he talked about computation or pre-processing near storage, and ideas like that do kind of feel right about here, right? Of course, more analysis and more work is required to make sure that that actually works. But so a lot of pre-processing happens, and pre-processing, this one is very important. They tend to pre-process on very self-contained data, meaning that they don't communicate across data workers. So they batch it in a particular way that each DPP worker works on its own portion. It doesn't require anything from anybody else. This is very interesting. I don't completely understand how they can do it based on some of the computations they can do, but I'm sure they're doing it, right? Okay, so we've talked, I hope we have answered why data ingest is important, how it is important in DLRM context, how Meta thinks about its AI pipeline, and how SSD has started figuring into the picture with the pipeline itself, correct? So the next one, I wanted to talk about is MLPerf training benchmark. So this comes from our performance group from Sujit and a lot of his team members. So MLPerf training benchmark suite measures how fast systems can train models to a target quality metric. And each benchmark is defined by a data set and quality target. I think I put a I should have put a plug. Oh, there it is. So please go check out mlcommons.org, and there is a lot of benchmarks, there are a lot of results, and they are updating it. Micron participates in it, and we are kind of using that to compare and contrast against what we see in literature to what we can see from these benchmarks, right? So that's how we can learn what storage needs to do, what SSD needs to do as we go from generation to generation, how things change, what do we need to kind of think about, and how problem statements have to be prioritized. So we took the DLRM model, a large model with 13 numericals, so this is in no way to the scale of 12 trillion models, right? So absolutely not, right? We don't have the capacity to do this. So this is from the benchmark with 13 numerical, 26 categorical, and 1 true label. That's whether the user clicks or not. I think you can read about the details about the model, how much VRAM it takes, and we use, I think, 4 A100 GPU HBM capacity is required. The data set, I think, if I'm not mistaken, it comes in like that NPZ, NumPy format. But when you turn it, the pre-processing will turn it into another format, like a Parquet format. And a total data is only 1 terabyte. Again, if you see the data size, it's very tiny compared to the petabytes that they talk about. But hey, we have to start somewhere, right? The pre-processing, we do offline pre-processing because that's how it is structured today, MLPerf. Raw data is converted to columnar format and they put into a compressed Parquet format. Categories converted to so this category is converted to contiguous integer representation is part of the pre-processing, but not all of the pre-processing. And I've mentioned 2 of them, and I think we use the AMD 128 core processor to do this with NVIDIA A100, 8 of them. So what we can do really is we can run this workload, and we can trace it at the storage level. We can do other things as well, but at this point we are interested in the storage. So you can trace command by command, and then we studied what are some of the characteristics that come out of it. And I want to highlight, somebody really wants me for lunch. So, that's the thing. So let me set up this table a little better so that I know there is a lot of pink running around, but I hope it'll make sense. So this is all the details. So experimental setup, how it was set up, what is in storage. So this is one of the key questions that comes up, right? Like, do we store model parameters? Do we store state values? In this case, we are storing data set that is used for training, right? So that's what I meant by what is in storage. Runtime, percentage read volume, performance, queue depth, and stuff. So I don't want to focus on every single detail, and my point is not to kind of compare and contrast, although I've set it up that way. But really what I wanted to say is this first one, pre-processing is done with both GPU and CPU. By the way, NVIDIA talks about this, Facebook talks about, Meta talks about it in its paper. So we wanted to try both GPU and CPU. And then, of course, after the pre-processing, we also have to train, and that training is actually the benchmark, right? The second one, what we wanted to talk about is the payload. So what we typically see is whenever we see payloads, the payloads are pretty large. So in this case, it's about 512K, and about 90% of them are 512K, and that kind of trend is true for training on GPU, that is training and pre-processing. And then the writes, as you can see, a lot of people mentioned the sequential traffic. So we're also seeing something very similar. So about 85 to 95% of the world is sequential, and I don't think it should, it should be surprising, at least at the write side, because it's a lot of append-only writes. You don't go back, you don't change things. You kind of write another one at the end of it all. So this makes sense, but these writes, when I say they're sequential, they're not sequential as a single thread. That's the key, right? You have to be able to parse this data well enough to kind of get this sequentiality. And similar story with read, but a little less, meaning that as you look through the benchmark, there are portions where it is extremely sequential, and then there are portions where they're not sequential. Some of them we can completely explain, some of them we cannot explain. So there is more work going on in this area, but the point is, there's a lot of sequential large access going on, or you can think of it as a large payload access going on overall. And then finally, the other thing I wanted to talk about, which when storage is usually evaluated, right, what is the four corners and at a particular queue depth. That's not the real world use case at all, meaning sometimes you have very bursty traffic, kicking in 200, 300, 400 queue depth, and then you go off to like 10, 20 queue depth for some time. My point is that it is not sufficient that we should always look at the highest queue depth, highest performance. There's a lot of things that happen as you work through these workloads, and that's kind of the highlight here. There is a lot more detail as we work through them. Again, I don't want to compare these three and say why GPU is better than CPU. Those are some of the things that we are working on. Yes, we see the results, but how to explain the results is something that we will talk about later. Okay. All right, so I wanted to call out, as I said, Meta's DLRM pipeline with the DLRM benchmark. I wanted to kind of contrast these things. I've already done this. Pipeline processing, pre-processing is in line with training. So we're not doing that in the benchmark. It's offline. We do the pre-processing and then run the training. So that's why it's marked in red. Data stored in columnar format. Yes, of course, we don't know how they stripe, the details of how the data is laid out. We don't use RS encoding, erasure encoding. We don't do that. So it's red. But at least in principle, it's stored in a columnar format, a parquet format, where you can arrange columns a certain way. You can do data placement in a very specific way. Training consumes petabytes of data. I mentioned this. We only work with terabytes of data because that's what the benchmark is doing. And they've done a lot of key innovations have happened as far in data placement. Like I think the question about data, when we talked about columns, if 2 columns, 3 columns are being used often enough and they are accessed together, they do a lot of those data being placed together so that they can read large chunks out of this HDD. Now, you can also question my reasoning saying that, hey, they're reading it from HDD, but remember, it's a caching layer. Anywhere how you store in the HDD is how it's going to get stored for the most part on SSD as well, right? So it's not changing formats completely. So the call to action here essentially is create more representative benchmarks. We would like to know how data ingest, how storage participates in data ingest. We would like to know what storage has to do beyond capacity, beyond power. What does it have to do? What are some of the key characteristics that we have to think about as we go from generation to generation? And also, of course, on data placement and create an option to make pre-processing in line with training. Because the problem statement, if you go back to the initial one, the 50% or greater power consumption came from the fact that they were doing all of this inline. It just keeps chugging in through this pipeline, and they're doing it, and we are not doing it that way, right? So there are some differences, and in fact, this is not only our call out. I think it will help the entire storage industry to study and learn how the AI pipeline works, how storage fits into it, what does storage got to do with this, what are some of the key features that we have to think about. So it kind of helps by understanding how the underlying architecture looks like. So that's, and with that, I think I'm going to leave the key takeaways. It's just a way of kind of, tying a knot with the first slide. So this is the key takeaways and the call to action at the end of it. And that's my talk. Thank you. Any questions, please? This one? This one? Yeah, go ahead. Oh, okay, that's good. So these had some slight thing. I think these two were on one single SSD, and this was on 2. The training was on 2. The measurements are all on a single SSD. Yeah, they access, in the second case, right, the training case, there are 2 SSDs out of which we get data. It's striped across 2. In these, it's a single drive that is running. Yeah, this is 1 terabyte, and yeah. And the idea was not speed up. Our idea of studying was not just speed up. We wanted to see patterns. We wanted to see, what is the performance that we are going to ask from the ingest, because there is some processing happening on the CPU, happening on the CPU. It's not like everything just comes out and then does and then comes back in. That's not how it happens. So we just wanted to see the flow of traffic. That's why. Yeah. I mean, ideally one should scale this up, put it on Fabric, and study how this works. But that's what we are asking, that the storage community and data center provide us the data to be able to do that kind of scaling. Yeah, go ahead.
One of the things we started to see is that with flash being kind of a cache,
Yep.
persistent cache, we started to see a huge increase in terms of write writes per day or endurance.
Mm-hmm.
At least from the old days when we did CNN and similar things over to transformer and over to agents. What do you see?
So, I mean, I can only comment from the paper because they see it in their data center at scale. They do very specific things to reduce endurance. The caching thing, when they let it in, there is actually a DRAM cache above it. So the DRAM cache is the first host, and then when it comes down to SSD, by the way, traffics are mostly from SSD because of the capacity ratio. But there is like a one hop stage, right, like DRAM, and then if it is very hot or very cold, kind of something that you picked up is not very useful, it gets out of DRAM. And then they have some strategies where they also do something like first 10 times something needs to go in, they reject it. Like if somebody was evacuated and they quickly after they say, hey, I want to get in, they like evacuate 10 times, no, 10 times or whatever number before they get it in. But there are some very specific tricks they use to keep the endurance down. Very specific tricks they use. So clearly they are able to manage it. Yeah, go ahead.
Have they documented what happens if there's a failure in the middle of the training and the ingestion?
So that's a good. So that we didn't talk about that. Sorry, I think I missed it a couple of times. So what happens if there is a failure in training? My answer is going to be kind of more general because it's not specific to DLRM. I think the problem statement, in my opinion, is much bigger with LLM foundational model training because you're probably running like 16,000, 20,000. I think 16,000 is the number I remember from Meta's paper. 16,001 fails. You know what's happened. But the solution, I think, is very similar. It's all about checkpointing, the frequency of checkpointing. The frequency of checkpointing is dependent on how often the failures happen, like the rate of failure. And the checkpointing itself seems to, from their paper, seems to show that they go into the blob storage, not in like nearby storage. It goes back into that layer that they have. But they do agree, there are papers that talk about how you can do either, one of my colleagues forwarded a paper on asynchronous checkpointing, but there's another paper that I recall where the checkpointing is differential checkpointing rather than absolute checkpointing. So that's how they manage this whole thing, how this can be, yeah. And I guess they also have some software capabilities to kind of call upon other hardware items as, if some one thing fails, all right, I'll move it over to somebody else. No, not for this one, but they do mention it for the LLMs things. They do mention it in their paper, very detailed on what fails and everything, but not for this particular one. But it is an important enough problem that there are a couple of papers even during this time, which is 3-4 years ago, that they talk about. All right. If there are no questions, thank you very much for your time. You can come and talk to me or any of the things. Thank you.